Okay, this is experiment number 7, or op-amp experiment number 4 for course EGR-226 Circuit Analysis 2 Lab. And today we're going to take a look at a I to V and V to I converter using an op-amp. So I've got Circuit Maker open. What I'm going to do is open up the correct circuit here, and I'm looking for the I to V converter. There it is. I'm going to open this, and I think what I'll do is blow it up a little bit better so you can see this circuit a little bit better. So now I've got to find it and center it on the screen a little bit better for you. So there it is, and if I center it, here we go. Okay, so what you see here is a standard 741 op-amp. It has a 1K feedback resistor. Remember, as soon as you have any type of feedback resistor between the output pin 6 and the input pin 2, the inverting input, it turns out that we have what's called virtual ground. And the other thing we have is that the difference in voltage between the plus and minus inputs, the red and blue in this case, is equal to 0 volts. We also have R1, which is called a compensation resistor. In this case it turns out to be 23K. We don't have to have that resistor there, but it actually makes things a little bit better as far as the accuracy. You see the input over to the left is a constant current source. In this case it has 1 milliamp of current. And so what I'm going to do without further ado is to take and run this, and we'll see what we get in the output. There's a voltmeter there. Of course, we pop up on the screen over to the left. Let me blow this up. We have our voltmeter of 1000.0 millivolts, quite accurate I guess, and the output is exactly again 1000.0 millivolts, or 1 volt DC. So 1 milliamp in gives us 1 milliamp out. Now why this is because, again, the current will not go into the input terminals. Remember, the input terminals of the op-amp look like a high input impedance. So what happens is that the 1 milliamp current ends up flowing through the 1K ohm feedback resistor from the output terminal. And it turns out that if a 1K goes through, if 1 milliamp goes through 1K ohms, we have 1 volt. So the first reading would be that 1 milliamp in gives us 1 volt out. Now if I stop this and reset the current source, let's take and set it up to be now 2 milliamps. And run it again. Notice we get exactly 2 volts out. Now I'm not going to do all these. Let's take and say do 5 milliamps. So if I go and set this up for 5 milliamps and run it. Now notice we get 5.002 volts this time. Depending on how we set R1, the compensation resistor, it'll work over lower ranges. In this case, when we get to the higher ranges, it doesn't work as good. Not a big deal. You would probably take, if you were using one of these in practice, you'd try to figure out what your typical input current was going to be and modify your compensation resistor accordingly. Let's go and stop this. Go back, change this now to say 10 milliamps. Well, let's make it 15, make life easier. Go to 15 milliamps, hit OK, and run this. And notice in this case we got 15.01 volts. The error is getting progressively worse. We go to higher current. Again, that's a function of the compensation resistor R1. Now, 15 volts is actually what the power supply voltage is, plus or minus 15 for this 741 op amp, even though you don't see that here in the diagram. So what happens if I take and increase the current input higher than 15 milliamps? Let's take and go all the way up to, say, 25. Let's go up to 25 milliamps and see what happens. Now, in theory, before we do this, you might be inclined to say, well, the output's going to be 25 volts, and let's see what happens. And sure enough, it is 25 volts. Now, an interesting thing is, in practice, this wouldn't happen. You can only get out of this op amp upwards to, say, plus 15 volts. Turns out you can't get more out of a circuit that's run with semiconductors than the power supply inputs, except for certain exceptions like an oscillator, where you can get peak-to-peak voltages which are higher. But in this case, whoever came up with the model for this 741 op amp at circuit maker allowed it to take and output more voltage than it should be able to. Let's do one more here. Let's go and take this voltage and current rather source, and let's make it go up to, say, 50 milliamps. So now if we had 50 milliamps, and we'll see where the model was restricted. And so if I go to 50 milliamps, I can't get 50 volts out of this. And if I take and run it, well, look what happens. Simulation complete. Say yes. One or more errors occurred. You want to view the message, and we get a bunch of code that tells us what happened. Well, what's happened is, it turns out that whoever set up the model would not allow this to occur. The parameters of its operation, of the 741's operation, have been limited to a certain range, and therefore it just gives us no data for the output. Okay, so that's the current to voltage converter. By the way, if I took and changed the polarity of the current source, what would happen? It would just give us a minus voltage on the output. So now let's go and find the file that is the I to V converter. Here it is. Excuse me, V to I we want, rather, in this case. So here it is down here. And let's open this guy up. And we won't save anything there. And again, let's take and under the view, let's make this a little bit bigger so we can see it better. Again, we'll go to 200. And goes off the page again, so we take and center it, and here we go. This one here now is an op amp set up in this fashion, that in this case we have a 1 volt battery for the input. It's going into the non-inverting, the red plus symbol on the op amp. We do have a feedback loop from the output through a voltmeter, through a current meter rather, back to pin 2. So we have the necessary conditions for the zero voltage difference between the two input terminals of the op amp, and also the virtual ground consideration. So what that means is the 1 volt we put in, or whatever voltage Vin is, will show up on pin 2, the minus input. And if we have Vin on pin 2, that means we have Vin across Rin, and whatever the resistance Rin and the voltage of Vin is, using Ohm's law, we can figure out the current. So again, this is a voltage to current converter. So let's take and run this guy, and sure enough, in this case we get 1 milliamp. It's a little bit more than 1 milliamp. You notice there's no compensation resistor in this case, but we're not going to worry about that too much. So now if I go over to this guy and I take and highlight him and change him, let's make him 2 volts, and if everything works correctly here, we would assume that what we should get is 2 milliamps. And sure enough, we get close to 2 milliamps. So I'm not going to do all the values. Let's stop this guy again. Let's go and try, say, 5 volts, just to make sure, to give us confidence that this is the case, that it'll work. Hit OK. And run it, and sure enough, 5 volts. And you notice the error looks like it's creeping up here with more input voltage. So I'll stop this guy. Let's go to say 15 volts here. And now we want to think about, again, what we mentioned. It turns out that the power supply voltages are most likely plus or minus 15 for this device. And, well, plus 15 volts in divided by the 1 k ohm for Rn gives us 15 milliamps, and that's what we see. By the way, whatever the load is, our load there, in this case it's 1 k ohm, but the 15 milliamps would have to flow through our load no matter what its resistance is, up until certain, extents. There's a 15 volt drop across in this case right now, so now we're getting to limits of what the op amp will do for us. So we'll stop that guy. In this case, I'm going to go and up the voltage to, say, 25 volts. See what happens here. And if I go to 25 volts, hit OK, and let's see what happens. And we get 25 milliamps. Now, an interesting thing is the 741 op amp was designed in such a way that you cannot get more than 25 milliamps out of it. So let's see how the model works here. If I take and increase the VN voltage to something that most likely would cause this op amp to smoke, because it turns out that if I put 50 volts into the op amp, I would overwhelm the transistors inside that integrated circuit probably and burn them out. But we'll try it anyway. Again, simulation allows a lot of things that aren't allowed in practice. So now if I hit this, it kind of stops at 25.63 milliamps. Now remember, I just said that what happens is that we have a maximum current available out of the op amp. So the model that was set up for this op amp will limit the output current to just a little bit over 25 milliamps. So that's a fairly straightforward experiment, and looks like we can transform a voltage to a current or a current to a voltage using this device. Sometimes people would call this type of amplifier a transimpedance amplifier. Again, most amplifiers you put voltage in, you get voltage out, or maybe current in and current out. In this case, we put voltage in, get current out, or current in and voltage out. Again, a change in the type of unit. So that's it for this experiment.